Hello, in this video we are talking about section 8.7 on Taylor and Maclaurin series. We're in the day 2 lecture where we're working with Taylor and Maclaurin series. And the way that we are going to do this is by remembering that a Taylor or a Maclaurin series is just a specific type of power series. So all of the stuff that we learned in sections 8.5 and 8.6 that applied to power series also apply to Taylor and Maclaurin series. So in this video, we're working through example 2. We're going to use the fact that e to the x is equal to the sum from n equals 0 to infinity of x to the n over n factorial. This is the series that we obtained in example 1 in our day 1 from section 8.6, so just the previous example in this section. So we're going to use that series to evaluate the integral of e to the negative x squared dx as an infinite series by completing the following steps. So before I read those steps, I just want to explain that this integral right here is not something that you can evaluate using any of the integration techniques that we learned in chapter 6. If you try to think through those integration techniques, U substitution doesn't work, integration by parts doesn't work, trig substitution doesn't work, it's not a trig integral, and partial fraction decompositions don't work. So essentially this is an integral that you cannot evaluate analytically. That's using those integration techniques, but we will be able to express it exactly as an infinite series, which will then be a function that we can work with. So this is one of the nice things about power series and Taylor series and Maclaurin series, is that you are able to integrate more general functions now, and you still obtain an exact function that you're able to work with. It's written a little bit differently than what you might be used to, but it is something that you can work with easier. So now the steps that we're going to follow is, first we're going to find a power series representation for e to the negative x squared, and we'll determine the interval of convergence for that series. The interval of convergence is important because it tells us what x values we can say that the integral or e to the negative x squared, this function is actually equal to the power series. After that, then we're going to take what we obtained in part A and we're going to integrate it and again find the interval of convergence. In this video, we're just going to complete part A and we'll have another video for part B. So then for part A, what we need to do is we need to compare e to the negative x squared and e to the x. So this is the function that we have, and this is the function that we need. So what do we do to e to the x in order to get e to the negative x squared? Well, that means that we are going to substitute a negative x squared in for x. If we do that in the function here, then we will obtain our new function. So we need to do the same thing in the series. Now remember that substitution is the same thing as composition when we're talking about those algebraic techniques that we can use with power series. So we have e to the negative x squared must be equal to the sum from n equals 0 to infinity of e to the x had just an x there, so now e to the negative x squared must have a negative x squared there. We'll raise that to the n, and we'll divide by an n factorial. As far as this part of the problem goes, we don't necessarily have to rewrite it, but in order to complete part B, it is going to be a lot easier if we rewrite this series a little, so I'll go ahead and do that here. So I'm going to do that by splitting this up into a -1 times x squared. So that means that if I take this whole thing and raise it to the nth power, it's the same thing as taking both of those products and raising them to the nth power, which is the same thing as taking -1 raised to the nth power, x squared raised to the nth power, and now we can multiply our powers here so that we end up with a -1 to the n, x to the 2n. So that is how we're going to rewrite our numerator. We'll have a -1 to the n, x to the 2n, and our denominator, n factorial, will stay the same. So this is our power series, but we also need to find the interval of convergence. For the interval of convergence, I am going to recall some of the information that we talked about when we first saw substitution or composition with power series in section 8.6. So recall When using composition to obtain a new power series, the new power series has the same interior of the interval of convergence, but the endpoints may change, so they must be checked individually. All right, so we don't have to start from scratch here with applying the ratio test, although that is an option if you would like to do that. What we're going to do is use the interval convergence that we have for the original function, e to the x equals the sum from n equals 0 to infinity of x to the n over n factorial. So normally, if this were a brand new problem, the interval of convergence, or at least the radius of convergence, would be given to you. But in this case, since we're using the power series that we obtained in the previous example, you can look back at that example, or you can simply recall, oops, sorry, accidentally touched the keyboard for a second. Okay, so we can recall that the interval of convergence for this series is all real numbers. So that was negative infinity less than x less than infinity. Well, notice in this case, we don't have endpoints to our interval because the interval is infinite. So if we don't have endpoints, those can't change. Everything else has to stay the same. So that means that since the original interval of convergence is negative infinity less than x less than infinity, there are no endpoints so nothing changes. And the new interval of convergence is negative infinity less than x less than infinity. So in conclusion, we have e to the negative x squared is equal to sum from n equals 0 to infinity of negative 1 to the n, x to the 2n over n factorial, and this is true for all x values between negative infinity and infinity. And that is our complete final answer for part A. We will pick up with part B in the next video.